Okay, all right, and now let's proceed with the another section. After the table of results, you would normally have a discussion section. This is just an example. This part also should include some recommendations as well. But here you're just discussing that the experiment supported our hypothesis. From the results, we can see that as the voltage increases, the current also increases. And to ensure that the experiment was fair, we kept the resistance constant throughout the experiment, and that we did not change the material. So the same conductor material was used throughout the experiment, and we can see that our points fit in nicely. We do not have any outliers. So we can infer that there were no changes in the temperature of the wires. If there were, that will increase some resistance, and then it will decrease the current below the expected value. And then we calculated the resistance using the gradient, and so this is our calculation. We get 20 ohms, which is what we also measured here. Okay, and then you go to your conclusion. For great for those who are doing caps, this is emphasized over and over again, that the conclusion must include both the independent variable and the dependent variable. That's 1 mark. And then stated correctly, it's also another mark, so this is normally 2 marks. So we say that the increase in voltage results to an increase in current. So I have both the independent and dependent variable, that's 1 mark, and then the fact that I have stated it correctly, that if I increase the voltage, then the current also increases. Or you could say that since we have a straight line here, so then the straight line indicates a linear relationship. So we can then say that the voltage is directly proportional to current, or that the current is directly proportional to the voltage, provided that the resistance is kept constant. Again, there's also an emphasis that do not use directly proportional unless the relationship is linear. Let me just show you an example of what that means. Look at this table here. This is kinetic energy, which is half mv squared. If you plot the kinetic energy versus velocity, then the graph is parabolic. So question, if you can conclude if we're doing this experiment, and then your conclusion would be that as the velocity increases, the kinetic energy also increases. But you do not say that the EK is directly proportional to V. That's incorrect, because this is not linear, so it's parabola. Okay, so you only say that it's directly proportional if it's a straight line. That's why, again, we tend to, in the next video, we will look at linearization. If I plot EK versus V squared, then I get a straight line. But directly proportional means that the variable in the y-axis over the variable in the x-axis, when you divide the two, the number remains the same, in the sense that 8 over 4 is 2, 18 over 9 is 2, 13 over 16 is 2, 20 over 25 is 2. Okay. To close off, let's look at the ohmic and non-ohmic. So as long as the relationship between current and voltage at constant resistance is a straight line, then we say that the conductor is ohmic. In this case, let's say that the temperature suddenly increases, and then that affects the resistance. So if we start in this green line here, this is an ohmic part. So this one obeys Ohm's law because it's linear. As voltage increases, the current increases. And since it's a straight line, I is directly proportional to V on this green line. But then on this red line here, it's true that as voltage increases, the current increases, but I is not directly proportional to V here because this is not a straight line. So this is a non-ohmic. Let's say that if the temperature increases, then the resistance increases, so then the voltage value, the current values would be below what you expect. So then it forms this curve here. You could also plot V versus I, and then you will see the same effect, that you will have an ohmic part, and then as soon as the resistance change due to temperature, like the filament of the bulb, it is non-ohmic because the resistance also changes with temperature. So then this is a summary. Okay, I'm going to emphasize this again. Straight line, then you can use that this quantity is directly proportional to that quantity. If it is a straight line, this is I versus V, and there's a gradient 1 over R, and V versus I has a gradient R. V over I is R, I over V is just 1 over R, and these ohmic conductors, they obey Ohm's law, so that they have the graph is a straight line. And then non-ohmic conductors do not obey Ohm's law. So this is I versus V. And then you can see that as voltage increases, the current increases. That's a conclusion you can draw, but do not, again, use this direct proportionality here because this is not a straight line. This is a curve. So it's not linear. So the conclusion is just that the voltage increases, the current increases. And again, the gradient of a tangent is 1 over R. Or if you can plot it, V versus I. Again, here, as the current increases, the voltage increases. But this is a curve, so do not use directly proportional. So this is V versus I, and the gradient is R. Okay, thank you. In the next video, we will look at, inspired by these calculations here, and then we will look at the way in which we tend to not plot graphs of this nature, but then we do plot graphs of this nature to see the relationship between this quantity versus that. But when you do experiments, we prefer to have straight lines so that these calculations can have this type of calculations where we calculate the gradient and determine the quantity, which in this case is resistance. So let's look at that in the next video. Thank you for listening. Just put that here. Just remember this. I will see you in the next video. Cheers. Bye.